may use that down there. Well, I suppose for those of us and others who study caldera volcanoes, we all like to know, are they going to erupt again, and are we going to get a caldera-forming event? But such events are so rare, it's actually hard, to, obviously, to get a handle on such things. So often we're interested in looking at past deposits to get some sort of feeling for what state is the volcano in now. It may well be dormant or quiet, but can we say anything about where it's leading? Well, probably the answer is no, but we'll do this talk anyway. So in the case of amphiboles, they've been the focus of a lot of investigations because their composition can reflect temperature, but perhaps pressure as well. And of course, pressure gives us some idea of geometry and depth of magma prior to eruption. So the two things we'll focus on, what can we tell about the current state of the system from the older deposits that are available, and what conditions can we actually determine from amphiboles. In this case, we picked Amphibole because it's a common crystal that occurs in nearly all of the eruptions from this volcano over the last 40 to 60,000 years. And looking at geophysical signals, there's certainly suggestion that hot rocks are still beneath the ground. There's active geothermal systems, high heat flow and such like. So there is reason to believe that there could be future activity. Okataina volcano in the Taupo volcanic zone, a large caldera-forming eruption somewhere between 40 or 60,000 years ago. The age is sort of controversial. And since then, there's been a number of Plinian-style eruptions that we know of anyway, inside the caldera. And then in the last 26,000 years, we've got it fairly well constrained with two regions of active vents, or have been active, over that time, producing lavas, rhyolite lavas, and associated fall deposits. From our previous work, here's the caldera-forming magma. They're all high silica rhyolites, but notice after the caldera, we went to slightly less evolved compositions of higher temperature. These are iron titanium oxide temperatures. And then over the last 35 or so thousand years, slowly come back to higher silica, cooler magmas being erupted. We already know from zircon work that we've done ourselves and others like Bruce Charlier and Colin Wilson's group that there is a long-lived crystal-rich system down there. It doesn't mean crystals are growing all the time, but all of this activity could well have some sort of common parents, a common parent in that you can find old crystals in a lot of the eruptions, both the caldera-forming one and the post. Individual crystals, though, don't grow through this whole long period of 300,000 years. They grow for a while and there are hiatuses, and a lot of them stop growing well before they erupt. Well, that's a zircon record, and I've talked about it before. What do some of the other mineral phases tell us? Just a reminder, I suppose for myself, to tell you that these rhyolite eruptions are driven by basaltic intrusion. There's lots of evidence of associated basaltic fall and mingled magmas and other microscopic evidence. Now, to the Amphibole, if we look at each one of these is an analysis, and there's a lot of analysis underneath that you can't see, plotted against eruption age, and you can see that you get quite a diversity of compositions in each eruption with no trends in space or time. You can see no trend in time there. The space aspect is the fact that the vents have, we know the spatial relationship of the vents. Obviously, I can't show it on that diagram. Just some examples of some core rim pair analyses of 3 selected ones, but we could have selected others just to show that the crystallization paths are not in common. You can pick up a single chunk of pumice, and there's quite a diversity of crystallization histories just in the amphiboles. They're not all in agreement with each other. This is the dry bit, well, it is important, but we don't want to linger on it too long. It depends on what atomic substitutions that are going on in the amphiboles as to whether they're recording temperature or pressure or both. And also they reflect plagioclase crystallization that might be going on at the same time. If we plot the lumina in the +4 state against various other cations, we can get an idea of what are co-varying with each other. So it sort of gives us a general insight into what sort of substitutions are going on, and how good the fit of the line is gives you an idea of whether there is a one-to-one relationship, and the gradient of the line shows you the degree of what is controlling the variation in the alumina content. The alumina is often related to either temperature or pressure. Most people use it as a pressure indicator, but it's strongly controlled by temperature. Without all of the details here, you can see that some substitutions are clearly evident, and they're temperature-controlled ones. These are two prominent ones here. Here's an important pressure-controlled one. These sort of things can be demonstrated experimentally. I don't really see that as good evidence, if you look at that statistical information and that low gradient, that there's really any indication of what we would call pressure-controlled substitutions. And there may be, but it's a weak correlation, some relationship to the plagioclase that's growing at the same time. So from that, I would suggest that maybe we've got some temperature control, but maybe we don't have pressure control. And I feel you really need to look at data like that. You can't just go applying barometers and thermometers. So we tried the Radelphi barometer and thermometer because it's a well-used one, it's recent, it's based on a nice selection of data, and it doesn't require any assumptions about equilibrium with other phases. There's our whole rock compositions going from the caldera and through to modern. And you can see that in the black, these are the iron titanium temperatures. We had already seen that before, cooling with time. I've been getting cooler eruptions more recently. But in the white circles there, the amphiboles are a range of high temperature to low temperature through the whole sequence with no real trend. If you just accept the pressure calculations, you've got some very low pressures in my view. This could be only like 4 kilometres through the whole thing, but also high pressures too, all of the time. The black dots are a selection of other pressure-related data we have, like water contents and melt inclusions, just a scattering of data. Clearly, those pressure estimates don't fit with the amphiboles. And the oxygen fugacity, there's a big difference between iron titanium oxides and amphiboles. Of course, they probably crystallized at different times. But whether you'd have such a huge change in oxygen fugacity due to a crystallization event, I don't know. And there's just no time to talk about that in this talk. So, but it even gets worse. Then we do traverses within a single crystal. So this is a single crystal, and that's a single crystal, just two examples of big crystals. Big elemental variations, they immediately, if you use any barometers or thermometers, they immediately relate to big variations in temperature, big variations in pressure, and indeed oxygen fugacity. Well, maybe the fluctuating temperature, notice there's some pretty sharp boundaries between the zones too. Maybe that reflects, mafic intrusion, as long as the volatiles or the water content is right to allow the crystal to keep growing. So maybe that could be the case, but I'm not so happy with pressure varying in a one-to-one relationship with temperature. It would be a bit of what I call a 3 to 9 kilometre yo-yo going on, but I'm not, for me, intuitively, I can't really imagine a crystal doing that so rapidly and not being resorbed or something else changing. And besides, in my opinion anyway, the atomic substitutions are not consistent with pressure. So if you just simply use these sorts of barometers and thermometers, you could sort of perhaps get the wrong idea of what's actually happening. Comparing the Rhodielphi thermometer with another one that's quite well established, the Holland and Blundy one, which requires equilibrium with a plagioclase, so you need a plagioclase composition for comparison. There's not a one-to-one relationship, but we found if we use the more calcic plagioclases, we get a better agreement. So maybe that tells us that the amphiboles did crystallize at a higher temperature and they're not that much reflecting the final melt that they erupted in. I am running out of time. The less calcic plagioclases would be a better fit for equilibrium with the glasses using various methods that are available to test that. It's hard to draw a magma chamber, so every time I make a drawing of one these days, it seems to be more simple than the previous drawings I've ever made. We sort of imagine every eruption seems to be tapping a range of temperatures in the amphiboles. The melts would accumulate at the top in the more watery, cooler top, and maybe every so often when we get big-scale mafic underplating or remelting of the base, we get big overturn of the crystals quite rapidly, so they can't get back into equilibrium with each other, and that's why we're periodically tapping a range of amphibole compositions in every eruption. So diverse range of amphibole compositions, which in my opinion have very little to do with the melt. They're a genuine crystal cargo, a term that was introduced a while ago and certainly stands true for a lot of rocks. It seems like everything carries a cargo rather than an equilibrium assemblage. If we simply assumed that the alumina content in amphibole was a function of pressure, well, you'd probably get erroneous results. But if the temperature is correct from the amphiboles, it may not be, but if it is, we always seem to be tapping a wide range of temperatures. So have we got a big thermally zoned system that's so big that it's buffered from extraction events, magma extraction events? Even when big calderas form, perhaps we don't change the overall system that much. So maybe a near-stable thermal regime over the recent history of the volcano, which of course doesn't give us much clues to what point are we in its life now? Are we heading to more prolonged intracaldera activity, or are we heading up towards a big collapse event, or have we moved away? One thing is clear, that at least at this volcano, and I think people would say that that's true of some other volcanoes too, that external forces are controlling the tempo of eruption and probably the production of the melts. But then we have to ask the question, is it tectonics that drive basaltic volcanism, or is it basaltic volcanism driving the tectonics? But either way, the rhyolites are not driving the tempo. Thank you. Oh, it's gone red, so we've run out of time.
No, there's still time for questions.
Oh, I'll just talk a bit longer.
So, any question? No? Anything you want to add?
No.
No? Sure.
Thank you.
Thank you. So, now we will stay in New Zealand with our next speaker, who is... we will give an invited talk, Colin Wilson.
Thank you very much to the conveners for inviting me along. I must apologise for my voice. I have been the beneficiary of an Icelandic lurgi called courtesy of Magnus Gudmundsson, if he's here. Thank you, Magnus. So I hope I lasted through. What I would like to do during the course of this talk is to give you an overview and a snapshot of quite a wide range of work that has been done by myself, but more than anyone else by a whole group of very hard-working students and collaborators in trying to understand how a single volcanic system operates We are focusing mostly on its younger history. We've been very generously supported by the Marsden Fund over the last 3 to 4 years, and this is starting to try and bring the work together and make sense of a whole pile of disparate information. And the sort of big quick picture questions that we're trying to answer in this kind of work, and again, living on a volcano, you start to ask pertinent questions like, was that caldera-forming event a freak event, or is it the normal behavior? How rapidly do melt-dominant bodies, the things that actually erupt all over your landscape, come together? Because otherwise, what are you monitoring? Why are you monitoring? How long, how much warning might you have of an eruption? What are the recovery and renewal processes after a major eruption, such as the Ruanui? And is there a hangover? After every party, there has to be a hangover. Is there one at this volcano? And as background information, Taupo volcanic zone should be pretty familiar to most of you by now. The southern on-land extension of the Tonga-Kermadec back arc system onto the continental crust. The subduction zone transforms into this nasty, crunchy alpine fault part of the South Island. No volcanoes, just earthquakes. And within the Taupo volcanic zone, it's divisible both by age. It is contracted in the area encompassed by young vents over the last sort of 350,000 years. And it's divided geographically into northern parts, which are pretty regular, normal arc volcanoes and systems like White Island, and to the south, normal arc. And in between, there's about 120 kilometre by 60 kilometre area that is just quite extraordinary. In terms of its overall productivity, it stands up against the Yellowstone system, and part and parcel of what really intrigues us is why two big silicic systems with comparable outputs and lifespans should behave in such a totally different fashion. Within the central TVZ, there are a number of caldera volcanoes that we've identified. There's undoubtedly a whole lot more history and details to be sorted out in this environment. But one of the key aspects that is really central to our understanding of how the magmatic systems operate is the fact that instead of being in quite an ancient crustal area where you have lots of nice Precambrian crusts to provide leverage for isotopic systems, the New Zealand crust is young, very unradiogenic, and is actively being thinned under the Taupo volcanic zone, such that compositions with densities and velocity values appropriate to quartz feldspar compositions are only about 15 to 16 kilometers thick. Below there is still ongoing debate amongst the geophysicists and amongst the geologists as to whether it's anomalous mantle, intruded crust. The main point is that where we have evidence for interaction with radiogenic, evolved, by New Zealand standards, crust, it's got to be relatively shallow, in the top 16 or so kilometers. And within the zone, as Phil mentioned, we have evidence in the form of geothermal systems, these nice warm red colors here, shown up by shallow resistivity surveys. We have evidence for volcanism in the form of vents for rhyolite, andesite, basalt over the last 61,000 years. The main point is the rhyolite is coming out at a quite staggering rate, about 13 cubic kilometers per 1,000 years on average, and of that is only about a quarter of the natural equivalent, to about a quarter of the natural heat output. So if you take the flux through the geothermal systems as steady state, by the way, that is seawater and not the next new geothermal system to be exploited up on the Bay of Plenty coast, you're looking at about 50 cubic kilometers equivalent of magma being placed into the crust per 1,000 years. So in principle, we have a whole lot of magma to play with. A quarter of it comes out at the surface. What controls what comes out at the surface, its dynamics and its composition? That's what I'd like to focus on. Okataina, that Phil talked about, is up here. As you can see, the clustering and concentration of young rhyolitic vents here. And then what I want to talk about down here is Taupo and the associated area up here to the north that's called Maroa. used to be thought of as a caldera structure, but is now downgraded to just a dome complex. And with Phil's permission, I'll stick with 61,000 years for the age of the big marker horizon from Okataina. And this time volume arrangement is simply the simplest way of showing you what is an exceptionally complex eruptive sequence from this Taupo Mara area. Here's the Ruanui eruption, latest age estimate around 25.4 thousand years from new radiocarbon age estimates. And prior to it, we have a sequence of eruptions, including some at quite long time spacings, of different magmas, of which two of them I want to draw your attention to today because they turn out to be very, very important in our understanding. Some other eruptions here, which I won't go into. And then at this stage, as I'll show you, the magmatic systems and the eruptive products are geographically separated, but their host magmatic systems are active simultaneously. The Ruanui event happens, but subsequently the vents for these younger systems, a group of dacites, 3 groups of rhyolites, plus one more little spasm of this northeast dome magmatite, the vents geographically overlap, but they're separated in time. So the Ruanui eruption sees quite a fundamental change in the style and the modus operandi of this particular volcano. And I apologize for the clutteriness of this slide. In essence, all we're trying to do is to summarize here the evidence for the influence of that young, Permian or younger, grey wacky crust on the magmas using strontium. You could use other isotopes, but strontium just happens to be the one we have the most data for, versus some measure of magma fractionation. And what we find is here are the young sequences. Here is the Ruanui and its precursors. Here's the northeast dome type. They form subhorizontal arrays. So each group of eruptions appears to come from a source that has a commonality about it in terms of its degree of interaction with the crust, but which can vary quite widely in the degree of fractionation in any given magma batch that happens to hit the surface. And one of the first things you start to realize with this system is the idea that big caldera-forming magmatic systems basically act like a suction for all mafic magma, all magma coming into the base of the system, and exclude other activity. Just doesn't seem to work here. We have the different vents for, here's the Ruanui structure itself, the whole lake is the caldera from the eruption. Here we have 2 of the vents down here, established from tephrochronology and full deposit thicknesses, a vent sitting up here, and then 3 of the vents for the northeast dome magmatite. It's biotite bearing, crystal richer, very, very easily identifiable in the hand specimen and geochemically. And when you put the ages up, you can see that this system has been quite happily erupting every now and again, not by much. At the same time, we've had 2 eruptions here at very similar ages. The deposits from them both can be mapped separately. Where they overlap, there's virtually no signs of weathering or soil formation between them. A precursor to the big one at around 28,500 years, and then the Ruanui itself underneath here. So the presence of this monstrous magma system, we know it's monstrous because we know how much material came out at the surface, doesn't preclude a totally independent magmatic system operating in its own way less than 15 kilometers away, less than the thickness of the crust away. And to come back to these observations, there's 3 rather intriguing things that come out of it. And what has really started to drive our thinking is the uranium-thorium data from zircons from these eruptives, which we published a few years ago now, really emphasized that you have to deal with some strange things going on. The first one is that this unit, the Tihoi, and this one, which for sake, lack of a suitable Maori name to use it, just called the New Plinian, up here, erupted in very, very close sequence, have very, very similar zircon spectra, with an older peak around 95, 96,000 years, and a younger peak, and then an eruption age, as best we can estimate, around 45,000 years. So, does this mean your footprint is very large, has a very large big toe heading up here? Or do you allow for lateral magma transport in the crust? If it's the latter case, this is rather alarming, because what it means is that your vent structures are not necessarily the footprint of your magma body. And that's rather an alarming thought if you're relying on the vent positions for domes at Yellowstone or anywhere else at the Valles to represent where the magmas were being created and stored and generated at any given time. So these lines through here represent the young Taupo fault belt. Each of those lines is a fault scarp active in the last 20,000 years. Could it be that the magma was generated underneath here and laterally transported to erupt there? If so, how might you tell? It leaves no geological evidence behind it, necessarily. So we're coming back up now to the Ruanui, and I just wanted to put this in to act as a reminder that here's the Okataina, very, very similar chemically, mineralogically, in all its basic characteristics, isotopically, to the main eruption, but somewhat earlier, a paleosol, this bluish-grey unit, the Poihipi, that relates to a pair of dome-building eruptions just here, and then the main eruption here. This and this, this and this don't take any notice of each other, apparently, during the lead-up to the eruption. Then finally, the third aspect that we got out of the zircon model age spectra was the really alarming one, which is possibly why nobody's really picked up on it or critiqued it since, is here we have the Tihoi at 45,000, Okataina at about 28.5, Ruanui at about 25.5, and you'll notice they share a common root zone, are co-located, co-eruptive, so it's reasonable to suppose that the main magma source was underneath here. So they have a common root zone that comes through, and then they each have a smaller pre-eruptive peak. The size of that pre-eruptive peak, the histogram obviously is individual SIMS analyses from section. This is not surface profile data, this is cross-sectional data. But what you can do is take bulk samples of zircons and establish the age by TIMS techniques, multi-crystal TIMS techniques, and that allows you to see what the average age of the bulk zircon population is. And all three are different. Not a problem. The problem arises because this one was erupted around 3,000 years before this one, and it cannot be an aliquot of the same melt-dominant body that gave rise to the main eruption. They have to be separately generated, and the zircon data imply less than 3,000 years to generate the melt-dominant magma body, all 530 cubic kilometers of it. So how do we break into this? How do we try and understand just how fast these big systems can move? You know, hearing Krista's talk, realizing that the Yellowstone system may reactivate on a thousands of year time period. Could it be even faster? These are time periods that are not just of geology interest, they're of interest to the people living in the area, and in fact of Yellowstone, the entire US economy just about. And what we've done over the years is study the mineral phases in the Ruanui, which has between about 3 and 13% crystals. So it's generally crystal poor. And what you start to see after a while, and that crystal will be familiar to those of you who saw Bruce Charlier's poster yesterday, is that the quartz, the feldspars that we've studied, which have the blue cores, and the orthopyroxene, and this is work that is currently up on the poster of Aidan Allen and can be gone and seen this afternoon, is a commonality, core and then a euhedral oscillatory overgrowth. we would suggest that that core to rim relationship reflects a general process that affected many, many of the crystals that we see in the eruption products. The critical point to make, and this is particularly in contrast to the work that Gil Gualda has done at the Bishop recently, is that the cores are different sources. The feldspars are genuinely xenocrystic. They're coming from deep. They've experienced a strong assimilation event with more radiogenic melt, in other words, crustal melting. The quartz, the melt inclusion glasses, and this was the work I did with Yang Liu and Fred Anderson, those are more evolved. So the quartz and the feldspar are not coming from the same overall source. And the orthopyroxene, the cores chewed up, are more, in general, magnesium-rich. So those, again, are coming from less evolved sources than the quartz, but they're coming from consanguineous sources, so they're coming from a different place than the feldspar. So we've tried, the feldspar dating is problematic because of the presence of a diffusion barrier with the assimilation zone here, but with quartz, Bruce Charlier's poster yesterday gave some information from our NanoSIMS work. I want to focus on the orthopyroxene and cut a very long and complex story short because Aidan is far better than me at explaining it. If you take an orthopyroxene crystal from the Urunui, thin section it, and then do maps of different elements within the pyroxene, what you find is you can see a core zone which has now melt inclusions, mineral inclusions, has clearly undergone a very nasty point in its history where it became unstable, and then come into another point where it has stably grown. The critical reason for showing aluminium here is that the boundary in aluminium, a slow diffusing element, is sharp. The equivalent boundary across the A or the B axis in the crystal in magnesium or iron is blurry, and we can model it by diffusion. The C axis, in contrast, the aluminium is also blurry, so the stretching out of your magnesium values here is almost entirely due to growth zoning. It's not a diffusive phenomena. And what we've done is gone through a number of crystals, done the profiling, and fitted ages to them. And the ages are a bit startling. They agree with the zircon age. The model ages here are the individual values with their uncertainties. As Tom pointed out, you have to bear in mind that if that boundary between core and rim is an assimilation event or a heating event, you have to pick on a temperature or temperature history. What we've picked on is the final temperature, as estimated best by both iron oxides, pyroxene rims, feldspar rims. All the outer rims of these crystals are in equilibrium with the melt in which they now sit. And when you do that and take your individual values, the oldest age of the 28 or so that we've done is around 1600 years. The peak of the values is around 230 years at 770 degrees. With Bruce Charlier's model, we forgot to tell him we'd up the temperature by 10 degrees, so he got 320 degrees at 760 centigrade. Very, very similar figures. We probably shouldn't do any more work on the quartz in case we start to get more diversity. At the moment, we have excellent agreement. So it's consistent with the zircon histories. The zircon histories tell you about the age of crystals. They tell you nothing about residence times. What you have to do with zircons is to look at successive units. When you do that, that is when you start to see residence times coming out of the data that you have. It's a filling rate of around a cubic kilometre or more a year of high silica rhyolite. It's rather scary. Goodness knows what the geophysical signature would be if this is an accurate picture, but I think we might see something happening even if we didn't know where it was going to end. The eruption itself was a good one, decent size, the youngest super eruption on Earth, very, very complex. 10 eruption phases defined from the fall deposits and then very decent volume, coeval, non-welded ignimbrite and other pyroclastic density current deposits. The critical point that's always bugged me working on this unit is that it stops and it starts. Why? How? And in particular, the first phase, which gave rise to this white-coloured ash, is heavily bioturbated into the soil. There's a time break in there of something of the order of weeks to months, possibly even a year or two. So how do you deal with this? You've got 530 cubic kilometres of magma, hot to trot, ready to go, and you stop and start it like a committee meeting. It's just ridiculous. How do you do this? Well, the evidence that has been dug up by us and published earlier this year comes from a very detailed section that we managed to find, quite close to where the earliest of the vent regions were, again judged by full deposit thicknesses for the first two phases and then the third phase of the eruption. There's evidence that the vents were elongate down the southeast side of the lake. So we go to that location. Here's the full deposit sitting on its paleosol here. There's phase 2, phase 3, and there's no sign at this location of deep gullying or erosion at that horizon. And you go through and you collect a suite of pumice material, and as you go through, what you find is that there's a proportion given here of what's coloured in blue, and no prizes for guessing what it is. It's magma texturally, geochemically identical to our northeast dome magma type. The grain size distribution of this deposit tells you they were co-vented. So it's not as though we had a separate eruption active and happening to drop material into the deposits. They were co-vented. And so our overall concept is that during these early stages, the onset of the eruption was not mediated by the fact you'd created 530 cubic kilometers of gas-saturated magma. It's mediated by whether the tectonics allows the magma to reach the surface, and it mediates it through a rifting event that caused magma sitting somewhere up to the northeast to travel laterally through a dike structure and intercept the conduit and mingle in with the eruptives. You relieve the regional stresses with that dike emplacement, you snap the conduit shut, and then you reopen it when the stresses rebuild up. And if we take the AFAR triangle activity that's been going on for the last 8 or 9 years, that's of the order of 6 to 12 months, typically, for the kind of dike thicknesses we've been looking at. So we think the eruption is stopped and started by what Aidan wanted to call, and managed to get into print, the invisible hand. That leaves no geological evidence. You would have no clue were it not for this almost accidental traveller of your different magma type. And this, to a petrologist, should be utterly scary. It means you've got to go to the tectonics posters. It means you can't treat magma chambers in isolation from the regional tectonic setting and the state of stress locally in the crust. So finally, you've got to have a hangover after a party, certainly if you're one of my students. This is the caldera, huge big lake, 600 square kilometres. And we have a sequence of eruptions subsequent to that. Rhyolite starting from about 12,000, but 3 earlier day sites. Smallest is tiny, biggest is impressive, spaced at 20 to 6,000 year sort of intervals. How do we get to grips with this sequence? So I'm focusing on this later group, and the color coding is the early day sites here. Here's the latest little spasm of the northeast dome type, quite separate. And then 3 groups of rhyolite, of which we focus mostly on the day site and subgroups 1 and 2. Here's the critical thing. You would imagine, seeing as the vents, these are envelopes around the vents for all of those eruptions for the subgroups. They overlap themselves, they overlap the Ruanui caldera. There must be a mixing relationship. You've reactivated it. This is a classic resurgent, magmatic resurgence cycle. Yet the magmas, as best one can judge, are their own independent entities. There's no trace of mixing between the older, now defunct Ruanui system and the younger system. You've cleaned out the whole system. That's what it appears to be. The first units, the dacite, are very, very interesting, quite crystal rich, 15 to 20 to 25%, classic resurgent magmatism. And by pounding up, I think it was about 40 kilograms of pumice, Bruce Charlier managed to get 82 zircon grains out of it, which we cheerfully analysed. And all but 5 of those grains fit either greywacke, which we can match to the local terrains in the basement greywacke. For example, this has a very characteristic Cretaceous peak, or to magma from the earlier 350,000 year system. No more than 5% Arowanui age crystals. But the really scary thing is that those crystals, although scarce, are absolutely sharp and euhedral. They've not been altered by a dacite magma that would dissolve them, if you apply the Watson-Harrison modelling, in the order of 1 to 10 years. Is this telling us what the reactivation time of the volcano is 1 to 10 years? And then the younger ages, this is compilation of a data set from work by Simon Barker. All I want to do is to point out that when we do ages from the subgroup 1 rhyolites, we see possibly a pair of peaks. The uncertainties are a little tricky on saying they're genuinely different. And then the younger ones have a younger peak. So we're seeing a cyclicity of crystallization in the young material, but of those dominant peaks in the Arowanui, there is virtually no trace. You have cleaned the system out. So, is it a freak system? No, it's a simple extension of the magnitude frequency behavior of central TVZ over the last 61,000 years. It's not a freak, it's just an end member. The systems, this is the cartoon we've put together for the Arowanui system. Melt dominant body, the vertical extent, the horizontal extent is to scale. How do you build that in at most 1,500 years and mostly in less than a few hundred years? Is tectonics the answer? I don't know. That's what we're trying to find out. And subsequently, we have the early dacites, and because there is nothing molten in there, they can make it to the surface. As soon as you generate the first rhyolites, you create a density trap that's then modulating the compositions you see at the surface. So those early dacites and the earliest of the rhyolites are consanguineous. It's just simply that you've started to develop your rhyolite density trap in there. And yes, this system here just says, well, what the heck? I'm just going to keep on going. So the overall message from this, and it's a bad one for geochemists, is that all the geochemistry tells you one aspect of the story, but we've got to talk to structural geologists and understand what Moore diagrams and sigma 3 means. Tectonism, we think, is absolutely critical in this case. Whether it's critical at a place like Yellowstone or Long Valley has yet to be looked at or looked for. Another aspect is we're interested in trying to build up the overall picture of the TVZ batholith. We've got our own batholith. It just happens to be at about 700 or 800 centigrade and 4Ks down, so we can't visit it at the moment. What would we see if we went down there? How would we see its construction compared with, say, the classic Sierra Nevada granites or the Searchlight Pluton? The problem is that what we're seeing in terms of flip-flopping of magmatic systems is going just too fast for any plutonic system that's exposed at the surface to be able to see it. How we close that gap is a challenge. You can take a super eruption, a supersized magma body, develop it over tens of millennia, mobilize it in centuries and destroy it in one single event, and there is no hangover afterwards. Thank you.
We have time for 1 or 2 quick questions. Do we have any, what do we know about the current state of the system? Do we have any geophysics that tell us how it is down there?
The geophysics at the moment under Taupo is non-existent because of the presence of the lake. It's a very challenging environment. Further north, yes, magnetotellurics and other techniques have identified zones of hot rock, but we're not sure whether those are systems capable of developing. One of the main anomalies that Wiebke Heiser's work has identified is sitting under an area that hasn't erupted anything for 160,000 years. So there needs to be a bit of ongoing debate. The hope is that, yes, the development of the melt-dominant body would be seen in geodetic evidence, in seismic evidence, and that by the time this happens, we've got a reasonable clue as how to interpret the geophysical data.
Thank you. Thank you. We now move to a contribution of our convener, Ether Wright, who will speak about Mount Mazama.
Okay, I'm going to talk today about assembly of a large silicic magma chamber at Mount Mazama, or Crater Lake in Oregon. And I just want to point out that this is relatively large and relatively silicic. Colin just gave a talk on a system that's much larger and much more silicic than Mount Mazama. Okay, so Mount Mazama is located in southern Oregon, shown here with the red triangle on this figure. It's unusual in the context of the Cascades because it's one of only 3 identified quaternary calderas in the Cascades arc and the only Holocene caldera. The caldera-forming eruption happened about 7.7 thousand years ago and is depicted in the series of paintings shown on the right-hand side of this figure, in which 50 cubic kilometers of largely rhyodicytic material, but a minor amount of andesite as well, were ejected from the volcano. The removal of that material led to caldera collapse, forming this caldera structure here filled with the current crater lake today. Okay, so Mount Mazama is a great place for the kind of study that I'm going to present today because there's a really well-documented eruptive history over the history of this volcano, so over about 400,000 years. So the outline of my talk today, I'm going to speak to this long time series of eruption data that was largely studied and compiled by Charlie Bacon. This includes information on the spatial distribution of vents, the ages and compositions and volumes of eruptive units. And what I'm going to try to convince you today is that these data are consistent with quite simplified models of including 2 different things. The first is a magmatic lensing model. This is a mechanical model which relies on dynamic interactions between rising dikes at depth and an overlying pressurized magma chamber over a specified time interval. And here we'll look at the interval of time of 20,000 years that precedes the climactic eruption. There likely was also an increase in magma influx over this interval. And then second, I'll move to the larger question of what was unusual about the Mazama case, especially in the context of the Cascades. To do this, I'll look at a now coupled thermal and mechanical model, and I'll try to show that stable chamber growth required both pre-warming of the crust and local extension. Okay, so this graph here is quite busy. I'll try to walk you through it, but this is the crux of the data that I'm going to speak to today. The x-axis of this plot is time in thousands of years before present. Each of the dots shown on this figure represents an individual eruptive episode, where the size of the dot corresponds to the volume of erupted material. The y-axis here is the radial distance of the vent of each of these eruptive episodes from the inferred vent location of the climactic Mazama eruption. And the color of each of these dots correlates with the composition of, or the bulk silica content of each of the eruptive units. So warmer colors are more silicic compositions, and cooler colors are more mafic compositions. There are lots of interesting observations we can make from this data set. One of the first observations is that there's a general increase in the maximum silica content before the climactic eruption. In other words, we don't start to see the warmest colors, the true yellows, oranges, and reds, until tens of thousands of years before the climactic eruption. Second, we see more evolved eruptive units closer to the central vent. In other words, we see these warmer colors down further on the y-axis of this plot and cooler colors up higher. You'll also note that many of these dots down here in the lower portion, so closer into the central vent, are larger. The eruptive units are larger in size closer in. This kind of compositional and spatial information is consistent with the idea of the first model, which is a magmatic lensing model. Okay, so this magmatic lensing model is based on the idea that a magma chamber, shown here, can receive input from rising dikes from below, so melt input, from a footprint that's larger than its own planimetric area. This is based on work by Leif Karlström in a paper that he had in 2009. It relies on the idea that a high melt fraction body that is overpressured will generate deviatoric stresses that cause dikes below to reorient towards that magma body. In this process, there's a feedback between influx and overpressure that develops within the chamber, and an increase then in the capture radius of dikes from below. So what would the surface expression of this type of process look like? We'd expect to see that as the chamber grows, as overpressure increases, and as there starts to be a capture radius, we start to see a halo around that central vent, which lacks any monogenetic volcanism. So as growth continues, as overpressure increases, that halo should increase in size, mirroring the size of the capture area below. This continues until there's an eruption of sufficient size to decrease the pressure within the chamber, and the capture radius drops back to 0. Okay, so let's look again at our time history of eruption data. Now we'll just focus in on the last 50,000 years. So the x-axis here is just 0 to 50,000 years now, and what I want to point out is this spatial and temporal gap before the climactic eruption. So this is consistent with the idea of magmatic lensing, where we start to see a zone which increases in size towards the climactic eruption, reflective of that increase in capture radius, and then resets back to 0 after the climactic eruption. Indeed, if we use this magmatic lensing model for conditions that are relevant for Mazama in particular, we can find quite good consistency between the observed data and a model run. While I can't get into each of the details of these inputs, they're based on geology. I'll speak really quickly to our estimate of influx. First, let's look at this lower left-hand diagram. This is an estimate of flux over the entire time interval. We've seen some figures like this for other systems earlier this morning. The way that we calculate this is based on eruptive volumes over the time interval. We take a running average by specifying a time window. In this case, I'm using a 20,000-year time window across this time interval. We can then correct these fluxes by using the compositions of each of these eruptions, based on the idea that the flux into the system, so the dikes rising from depth, in this case, let's take a basaltic andesite as the input. So we correct the eruptive volumes using compositions and to try to get at an input flux, and we end up with a range of volumetric fluxes between 1 and 15 cubic kilometers per 1,000 years. I'll just really briefly mention that this is hundreds of bulk compositional analyses from Mount Mazama, including regional volcanics, Mazama volcanics, and individual glass analyses. And this is a sample melts model of a liquid line of descent that fits relatively well. Okay, so the other thing I want to mention is that there's an increase based on the eruption data of the flux towards the end of the sequence. Okay, so I hope I've shown that the data are consistent with this idea of magmatic lensing over about 20,000 years prior to the climactic eruption. But if we want to get at the larger question of what was so special about Mazama, we need to now look at how to stabilize that chamber. So now we increase this model to include both a thermal and mechanical perspective. This model still uses the lensing concept, but adds the thermal evolution of both the magma and the country rock. So now we have the addition of a viscoelastic shell around that high melt fraction magma chamber. This allows us to look at both the viscous and the rheological evolution around the chamber. So what comes out of this type of a model? Well, this was developed in a paper in 2010. The results are largely a function of the influx rate into the chamber, but are also a function of the geotherm and the depth at which that chamber is sitting. Some sample outputs resolve into 4 different distinct dynamic regimes. If influx is low, you could get a chamber that freezes. If the influx rate is high, then you could end up with a system that either erupts or results in runaway growth of the chamber. So if again we look at this for Mazama relevant conditions using melt fraction temperature curves from melts models like the one I showed a few slides ago, with the assumption that the input is hydrous basaltic andesite again. If we use a regional background geotherm at here, in this case we chose 10 kilometers depth as an average depth for the larger magmatic system. At that depth we're getting about just over 200 degrees Celsius. At the low end of the flux estimates that I showed a few slides ago, this results in a stable chamber, but we don't grow the chamber very much. Okay, so I'm going to show how input rate, the background thermal conditions, and regional extension then change this picture. So we don't have enough growth. Let's look at how increasing the input flux into the chamber, now we're at the upper end of those estimates from the flux calculations I showed you several slides ago based on actual eruption data. We start to grow the chamber, but very quickly the system erupts. If we now try to figure out how to stabilize that chamber, let's look at a change in the temperature of the background. So now, without getting into the details of how this occurs, let's just set the background temperature to 300 degrees at this depth. Again, it leads to eruption, and it takes getting up to 400 degrees for a background temperature before we stabilize the chamber. And indeed, in this case, it grows in a manner that would be consistent with growth towards that caldera-forming size. Okay, so you require an influx, or an increase in the flux in order to grow the chamber, but you also require pre-warming in the area in order to stabilize that chamber. Well, how does this compare to other Cascades volcanoes? This is a table, a compilation from Wes Hildreth's professional paper in 2007, where here are several different eruptive centers in the Cascades. And I just want you to focus on this column here, which is essentially an eruptive flux, like the calculation that we did for Mazama. And you'll see that Mazama, the flux is not particularly high in comparison with many other Cascades volcanoes. In fact, it's low in comparison with several other centers. And this is important, especially in the context of longevity of some of these systems. Let's take, for instance, Shasta with a comparable eruptive flux. And the time history of volcanic activity of Shasta is up to 600,000 years. So what else could be happening at Mount Mazama? All right, here I'll speak to the effect of extension. Now, in this thermomechanical model of chamber evolution, we use the elastic pressurization timescale, tau here, which is a function of the chamber volume over the input flux, scaled by the maximum critical pressure over the Young's modulus as a criteria for stability of that chamber. If we now, in a very simplified manner, look at what the effect of extension would be, we can see this is epsilon here is extension rate. As you increase the extension rate, you increase the elastic pressurization timescale. In other words, you help stabilize that chamber. So what does this mean? Effectively, an increase in extension does something similar to increasing the background temperature or the pre-warming in moving things from eruptive to stable behavior. Okay, so in conclusion, I kind of roared through a comparison of our really great data set for Mount Mazama, 400,000 years of eruptive history. And I hope I showed that the spatial and temporal information, specifically this gap in eruptive data, is consistent with the idea of magmatic lensing. However, I also showed that over a longer time perspective, you need high input rates in order to grow that chamber, especially towards the end of the sequence, but that stable growth requires both pre-warming of the crust and probably also local extension, which is observed in the Mazama area. Thanks.
We have time for 1 or 2 questions. I was just wondering if you modify your magma chamber that attracts the dike is spherical.
Yeah.
If you modify the shape, what will happen?
Yeah, okay, so right now we're just starting with a very simple geometric assumption of a spherical chamber. The person to ask more detail about this is Leaf, but he tells me that a cylindrical chamber doesn't change things much, but that depends on the aspect ratio of that chamber and is probably the subject of our future work. Yep. Yeah, that's possible. I mean, clearly the chamber did not look like that. It wasn't a sphere. The outline of the caldera itself, in some places we get calderas that are very elongate. This is a pretty equant, size or shape of a caldera itself. If that mirrors the chamber, then maybe that tells you something about the chamber dimensions.
Okay. Our next speaker is Gualda, who will speak about Bishop Tuff.
When it gets yellow.
When
Okay.
it's red, you have to jump to conclusion.
Okay. All right. Hello, everybody. Can I go? Thanks for being here. I want to talk to you about work I've been doing with Mark Giorso over the last couple of years, trying to use phase equilibrium constraints to understand magma bodies, in particular the Bishop Tuff magma body. Given the audience here, I don't need to tell you that super eruptions are scary and incredibly fascinating events that have continental to global consequences. So I'll move on. And I'll tell you that the focus of my presentation today is on the structure, and many presentations, in fact, is trying to understand the structure at the subsurface of these magma bodies. And so what we're going to do today is try to use phase equilibrium constraints to get to the structure of the Bishop Tuff magma body. The Bishop Tuff will be familiar to many of you. It's located in central eastern California. Here is the Long Valley caldera. And the Bishop, as many of you will know, the Bishop Tuff deposits are divided into two main packages, one to the south and east, and one to the north, separated by the Glass Mountain, which is an earlier volcanic edifice that served as a topographic hide during the deposition of the Bishop Tuff. In the south, we have, in the Bishop Tuff, you have the underlying fall units and interbedded ash flow units overlain by massive ash flow units, while in the north, you basically exclusively see these massive ash flow units with the discrete, at least discretely present fall units being absent. The Bishop Tuff has come to our attention to a large extent to the seminal work of Hildreth in the late 70s, who conducted a detailed study of the Bishop Tuff. Two things I want to point out to you here in this specific diagram is the fact that all rocks in the Bishop Tuff are characterized by a multiple saturation in several minerals, quartz, two feldspars, magnetite, ilmenite, and zircon in particular. Some of the rocks in the Bishop Tuff are pyroxene bearing, while others are pyroxene absent. The pyroxene absent rocks were the rocks that appeared first in the eruptive sequence, so I'm going to refer to them, as has been done for a long time, as the early erupted Bishop Tuff, and the pyroxene bearing rocks I'm going to refer to as the late erupted Bishop Tuff. And what we're going to do is try to contrast and try to understand the distinction between these rocks using phase equilibrium constraints. The striking result, familiar to many of you, is that Hildreth found was this array of temperatures and oxygen fugacities derived from iron titanium oxide. So really suggested that there was some thermal gradient within the magma body of the Bishop Tuff, because the early erupted units give these lower temperatures, and the higher temperatures are coincident with the late erupted material, and there seems to be some progression with the stratigraphic position. Hildreth inferred that the Bishop magma body was characterized by some thermal gradient. Comparing this thermal gradient, look here, these are diagrams from Hildreth's paper in '79, and you can see that plotted on the x-axis is the temperature as inferred from iron titanium oxides and the compositions of several minerals, both in terms of major and trace elements and minor elements. And what you see is this seemingly gradients in composition as a function of temperature as retrieved from iron titanium oxides, which led to the idea of a thermally and compositionally stratified magma body. And because each pumice class has its own identity in terms of temperature and composition of the phenocryst, also gave the impression of a stably stratified magma body. So here's what we're calling the standard model, one in which this has become, the Bishop Tuff, the classic example of a stably stratified, both thermally and compositionally, magma body, order at least 600 cubic kilometers, with thermal and compositional vertical stratification, and with stable stratification, with, as many of you will have argued in the past, brings some problems as to how to maintain, how to create such vertical stratification. It's important to point out that the Hildreth's model really didn't have any direct pressure estimates, or at least not very tightly constrained. And the main pressure estimates for the Bishop Tuff come from the work of Fred Anderson, Paul Wallace, and students at Chicago, studying melt inclusions and the fluid saturation pressures within those, of a characteristic of those melt inclusions. And what is striking about this diagram from Paul Wallace's paper in 2009 is that you see two quite different arrays of data. On the low CO2 range and variable water range, you see the early to middle, which is all early erupted in my nomenclature, array, which shows consistent with some progressive, with the eruption of progressively, material coming from progressively deeper regions, while the late erupted data shows a much more scatter, seems to be different compositionally, and for which the case for fluid saturation is more difficult to make. So the interpretation has been made that really it's the highest pressures that are probably only significant, such that this data can be reconciled with what we call here the standard model. So what we wanted to do, one more piece of background. Last year, Mark Giorso presented work that we've been doing using iron titanium oxides to derive titanium activity in the melt from which these iron titanium oxides crystallized. And what you see here is that in terms of titanium activity now on the y-axis, you see this, again, this very striking array of titanium activity as a function of temperature. This is in what the colored lines here are titanium activities calculated from melts. And so you would expect, this array is very striking because what you would expect is with lowering temperature, you would approach titanium saturation, so you would expect negative slopes on this diagram, while the Bishop array shows this very striking positive array. And what the melts calculations show is that none of these iron titanium oxides seem to be in equilibrium with melts that are characteristic of the Bishop Tuff. We are plotting here a range of pressures, a range of compositions that are even beyond what is representative of the Bishop Tuff. So this puts into question whether the iron titanium oxides are recording pre-eruptive conditions for the Bishop Tuff. Given that this is the backbone of the standard model, this array, what we want to do today is try to look at other sources of information on pressures and temperatures of crystallization to see whether there is any support for the standard model, as I call it. Again, I want to emphasize to you the fact that all of the rocks in the Bishop Tuff is saturated in quartz 2 feldspars and zircon. And what we're going to do is we're going to take advantage of the database of melt inclusion data, credible database that Fred, Paul Wallace, and students have put together. I'm not going to bore you with the results of all of the details of this database, but there are dozens of melt inclusion analyses of various kinds. In terms of temperatures, we can use zircon saturation to yield temperatures of crystallization. Basically, two variables of interest here, zirconium in the melt inclusion, and some parameter that describes the major composition of the rock. And what you'll see here is that, maybe surprisingly, the zirconium concentrations of both early and late erupted magmas are very similar to each other at about 80 to 90 ppm. In every diagram, red will mean early erupted, blue will mean late erupted, if I forget to mention that later. So the zirconium concentrations are very similar to each other. The compositions of early and late erupted magmas are very similar in terms of major elements. So the M parameter is also very similar, which results in temperatures that are very similar to each other. And there is no sign of that strong thermal gradient of about 100 degrees as inferred from the iron titanium oxides. This is in quite good agreement with rhyolite melts calculations that we've made and published over the last year, showing that both early and late erupted magmas crystallize essentially isothermally or have a very strong eutectic behavior and crystallize at temperatures on the order to 750 to 760 degrees, quite in good agreement with the zircon saturation data. In order to try to get to pressures, we're going to show you 3 attempts that we've made. Last year at this meeting, I presented some data arguing that silica in the glass is a good measure of the pressure at which crystallization was taking place for magmas, for melts that are in equilibrium with quartz in 2 feldspars. And what I'm showing you here is the composition of the melt inclusions. Again, unimodal distributions with an average that is essentially identical for both early and late erupted magmas. We've known for a long time that the positioning of glass or melt compositions within the haplogranitic ternary gives you is very sensitive to pressure. And so if we can plot the melt inclusion compositions onto this ternary, we have some indication of crystallization pressure. I'm using here the projection scheme of Blundy and Cashman, 2001. And what you can see, again, the red dots are early erupted and the blue dots are late erupted melt compositions. And what you see is that there is no evidence that the late erupted magmas may have come from deeper than the early erupted. If anything, there is some indication that the late erupted magmas may have equilibrated at slightly lower pressures than the late erupted magmas, than the early erupted magmas. Sorry. Finally, we've been trying to refine this data by looking at using rhyolite melts calculations to constrain pressure, and we can do that because these are melt inclusions entrapped in quartz. And so we know that these melt inclusions at their liquidus must be multiply saturated in quartz and feldspar. These colored curves here are the temperature of saturation as a function of pressure, and what we seek for is the pressure at which multiple saturation occurs at the liquidus, and we can basically infer a pressure of crystallization. Can't get into further details, but what you can see here is we apply that to early erupted melt inclusions and late erupted melt inclusions. And what you see again is unimodal distributions with very similar averages for early and late erupted Bishop Tuff. So the bottom line here of this analysis is if the standard model were to be correct, this idea that early erupted that this was a vertically stratified magma body, you would expect to have low pressures where you have low temperatures and high pressures where you have high temperatures. And what you're going to see from this plot is quite a strikingly different scenario in which you have a limited range of temperatures and somewhat of a larger range of pressures. Maybe some of this larger range is due to relatively large uncertainties. But again, no indication of any difference between early and late erupted compositions or magmas having come from different parts of the crust. This is confirmed by, if you take the pressures derived from the melt inclusion data at face value, again, you get this overlap in pressures. And what is even more striking, looking in more detail into the compositions of the melt inclusions, is what you see is rather than a gradient in composition, what you see is bimodal distributions, both in terms of major elements, minor elements, and volatile elements, suggesting that there is some compositional separation or some compositional individuality between early and late erupted magma. Even the data of Hildreth on the minerals bear those conclusions. This is calcium and plagioclase, barium and sanidine, and I could keep doing this until you were sick of looking at histograms. But basically, the bottom line is major elements, major minerals, and accessory minerals, both in terms of major elements, minor elements, volatile elements, all show some degree of this chemical separation between early and late erupted magmas. So what we want to suggest here today is that there's little support for the standard model as originally suggested, and what there is more support for is the idea of 2 laterally juxtaposed magma bodies, one representative of the early erupted another one representative of the late erupted magma. There is stable stratification. If we believe in the evidence for stable stratification, then there would be some evidence that these are actually physically separated, and that helps explain why you don't see this mixing between early erupted and late erupted material without having to invoke some difficult ideas about how to maintain a vertical stable stratification. To conclude, I'll leave you with the idea that when we look at early and late erupted Bishop compositions in terms of their phase equilibria characteristics, what we get is that they all crystallize a relatively tight range of temperatures and a relatively tight range of pressures that are about the same for both early and late, that there is no continuum in composition, or it's much more limited than originally thought. So this gives the suggestion of laterally juxtaposed magma bodies rather than the archetypical idea of a vertically stratified magma body. Thank you.
One very short question, yes?
Sure. Sure. So Paul's comment is to the fact that maybe melt inclusions that are in the cores of quartz crystals in the late erupted are quite different from inclusions in the rims of late erupted crystals, and that the late erupted, the rims seem to be consistent with this thermal gradient. And I don't have any problems with that, because what I think this represents is that the cores of the crystals are representing the pre-eruptive history, while the rims are represented actually the eruptive history of the magma body. So something happened before eruption and changed the structure, changed the conditions, and that's what's possibly being recorded by the iron titanium oxides. Almost fell. Thanks.
Thanks. So our next speaker is Catherine Watts, who will speak about the Caetano magmatic system.
Okay, so today I'm going to talk about the petrologic evolution of the Caetano magmatic system, which was source of the 1,100 cubic kilometer Caetano Tuff 34 million years ago. The Caetano caldera has since been dissected by large magnitude basin and range extension, which has provided really exceptional exposures into the inner workings of a large caldera system. Now, the exposures of the Caetano caldera may not only be useful and important for reconstructing the key magmatic processes that led to eruption of the Caetano Tuff, but also potentially for better understanding other comparably large caldera centers around the world that are less well exposed. So Caetano is located in north-central Nevada. It's one of many of mid-tertiary aged caldera centers in the northern Great Basin. Restored caldera dimensions after removing extension post-dating caldera collapse yield a caldera of about 20 by 18 kilometers, and this was source of the 1,100 cubic kilometer Caetano Tuff. Now, Caetano is interesting in that it not only produced one of the largest known tuff eruptions in the western U.S., but also because it's spatially and temporally correlated with very large-scale gold deposits. So Cortez is a Carlin-type gold deposit locality that's immediately northeast of the Caetano caldera boundary and contains an estimated 15 million ounces of gold. So Caetano is an interesting and important research target for many reasons. So now we'll talk a little bit about the geology of the Caetano caldera. This is a geologic map that was published by Joe Colgan, Chris Henry, and David John in 2011. You can see that the present extent of the caldera is very elongate in nature, owing to about 100% east-west extension that post-dated caldera collapse. The light pink color shows intracaldera Caetano Tuff. There are also darker pink colors here showing the 2 generations of resurgent granitic plutons that intrude the center of the caldera. There's silicic ring fracture intrusions preserved along the margins of the caldera. In the northeastern wall of the caldera, there's a tuff dike that sourced the early eruption. And also near this area is Cortez, which is the Carlin-type gold deposit locality that I had shown on the previous slide. So restored caldera dimensions after removing about 100% east-west extension yield a caldera that's about half the size of the current extended size of the Caetano caldera. So now let's take a look at the cross-section. So both a present-day cross-section at the top and then a restored cross-section restored for extension and with slip restored along normal faults. The caldera is broken into a series of east-tilted fault blocks that expose more than 5 kilometers of the upper crust. This includes over 4-kilometer thickness of intracaldera tuff, 2 generations of resurgent granitic plutons, silicic ring fracture intrusions, and pre- and post-caldera andesites. So truly exceptional exposures of a large ash flow tuff caldera. So I'll now show some photos so you can see what some of these field relationships look like. In the foreground here is the caldera floor, which is a Paleozoic sandstone and chert pebble conglomerate. It's overlain by a very thick sequence of intracaldera tuff. So Mount Caetano that you see there consists entirely of the lower unit of the Caetano tuff. This was in part sourced by a tuff dike along the northeastern caldera margin. And you can see in this photo has very large inflated pumice towards the center of the dike. A Caetano tuff can be divided into 2 members that are separated by a distinct cooling break. The lower unit, which is a thick compound cooling unit, and the upper unit, which consists of multiple thin cooling units. The Caetano tuff is compositionally zoned. So this is a plot here that shows the stratigraphic position in meters above the caldera floor for intracaldera Caetano tuff samples versus a variety of parameters, including silica content, titanium content, liquidus temperatures, and crystallinity. At 3,500 meters above the caldera floor is a major cooling break that separates the lower and upper Caetano tuff units. But if you take a look at the left 2 panels, what you can see is that stratigraphically below the cooling break is a compositional break. So there are clearly 2 different compositional groups within the Caetano tuff. And if you look at the averages, and there are 1 standard deviations for these compositional groups, what you can see is that the base in the middle part of the lower unit have very evolved compositions, about 77 weight% SiO2. And then there's a compositional step to less evolved compositions in the upper part of the lower unit in the upper Caetano tuff to a low silica rhyolite composition of about 73 weight% SiO2. Also plotted on this figure the intrusive plutonic rocks so that you can see how they compare. So they're just arbitrarily plotted here in the red squares to compare them. And you can see that these plutonic rocks are compositionally equivalent to the least evolved parts of the intracaldera tuff. So titanium content, we see the same thing, going from more to less evolved compositions, with the plutons being compositionally equivalent to the least evolved portions of the tuff. If we look at the liquidus temperatures, you can see that these overlap within their 1 standard deviations, but we are able to resolve a thermal profile that corresponds to the compositional profile going from lower to higher temperatures up sequence. And then if we take a look at the furthest right panel, crystallinity, interestingly what you can see is that throughout the entire 4-kilometer thickness of intracaldera tuff, the crystallinity remains very high and very constant at about 40 volume%. So despite the compositional zoning, the crystallinity is very high and constant. We also observe zoning in the trace element data. So here is a spider diagram showing rare earth element concentrations for different parts of the Caetano caldera. So the warm colors show the least evolved parts of the caldera, which are the plutons and the upper Caetano tuff, and the cool colors show the most evolved parts of the caldera, which are the lower tuff unit and the tuff dike. Average rare earth element concentrations indicate about 40 to 44% fractional crystallization to generate the most evolved Caetano composition, which is the tuff dike, from the least evolved, which are the plutons. So now let's take a look at some mineral zoning within the Caetano caldera. The left panels show plagioclase compositional histograms, and on the right, orthopyroxene compositions. So looking at the plagioclase data first, what you can see is that the dominant mode for the plagioclase compositions in the base of the lower Caetano tuff unit and the middle of the lower unit have very evolved compositions, about anorthite 10 mole%. And then we see a distinct shift in the compositions to less evolved plagioclase compositions at the upper part of the lower unit, and the upper unit shifting to about anorthite 30 mole% for the dominant mode. So corresponding to the major element compositional zoning that we observed going up this intercaldera sequence. If we look at how they compare to the resurgent plutons, which are shown in the red histogram bars just to the right, you can see that these two generations of resurgent plutons have also these less evolved plagioclase compositions of about anorthite 30 mole% that corresponds to the least evolved parts of the intracaldera tuff. So at the plagioclase data, we're seeing a normally zoned upward sequence going from more to less evolved compositions, and that the upper tuff is compositionally equivalent to the resurgent plutons. Now if we take a look at the orthopyroxene data, so again starting at the base of the lower unit and the middle of the lower unit, this time what you could see is that the orthopyroxene compositions are actually less evolved at the base and then go to more evolved or lower Mg numbers up sequence. So this is reversely zoned and decoupled from the plagioclase trends. And I think that this may be due to incorporation of more juvenile pyroxene crystals from pumice clasts, which were observed in the more evolved lower Caetano tuff unit. The pyroxene is fairly sparse and generally occurred as isolated crystals in the ground mass, but there is petrographic evidence for them also occurring in these more juvenile pyroxene crystals. So I think that these were partially disaggregated or fully disaggregated, dumping these more juvenile or less evolved crystals into the more evolved Caetano tuff melt, and that's what's the cause of this decoupling that we see from the plagioclase trends. We also see zoning within the sanidine crystals in the Caetano tuff. What we observe is that cathodoluminescent zoning corresponds to sharp compositional gradients in barium concentrations, indicating recharge within the Caetano magma chamber prior to eruption of the Caetano tuff. So the plot on the left shows barium concentrations obtained for two traverses across the same compositional boundary obtained during separate analytical sessions. You can see there's quite good reproducibility of that data, going from overall lower barium concentrations to higher barium concentrations up to about 17,000 ppm in the CL brighter domains. Simple 1D diffusion modeling yields timescales that range from hundreds to thousands of years to generate the observed profiles. And what we observe for the majority of the crystals, the majority of the sanidine crystals, is that they're characterized by CL dark cores that are mantled by progressively CL brighter and barium richer overgrowth rims, recording multiple recharge events. So if you look at the image of the crystal on the right, you can see it goes from a CL darker core and has several discrete boundaries that you can resolve as the rims become more CL bright and more rich in barium. Here's another crystal that shows a similar pattern. Again, you can resolve multiple compositional boundaries going from overall CL darker cores to CL brighter rims. In this large crystal with this longer traverse here, you could see the same thing going from about 6,000 ppm barium up to almost 2 weight% barium in the outermost rim. And again, multiple compositional steps that are resolved. So in conclusion, we see that the Caetano tuff is compositionally zoned, both in terms of its major and trace element whole rock chemistry as well as its mineral chemistry. It goes upwards from high to low silica rhyolite compositions, and the least evolved parts of the tuff are compositionally equivalent to the resurgent plutons. So this supports the role of the linked volcanic plutonic components in caldera settings. There is evidence for multiple recharge events. However, these events did not lead to formation of a compositionally homogeneous magma reservoir prior to eruption of the Caetano tuff. Therefore, the Caetano tuff does not fit the paradigm of a reactivated mush that's necessarily well mixed due to convective stirring accompanying recharge. It's exclusively crystal rich, but it also preserves compositional gradients. The complex mineral zoning and textures and zircon geochronology indicate prolonged and complex episodes of magma assembly and growth, yet the argon geochronology reveals rapid eruption, caldera formation, and intrusion of resurgent plutons at 34 million years within error of their ages. And the last point I'd like to make is that generation and eruption of more than 1,000 cubic kilometers of compositionally zoned crystal-rich rhyolite does not fit the prevailing supervolcano models for crystal pore rhyolites derived from crystal mushes or compositionally homogeneous crystal-rich dacites, or so-called monotonous intermediates. Therefore, the Caetano tuff may be an important new end-member for us to consider in large-volume rhyolite genesis in the shallow to middle crust. So, thank you.
Question?
So I've started looking at this with only one part of the intracaldera tuff, so I haven't extended that investigation yet to other parts of the tuff, so I don't know yet. But yeah, it's continuing work. So the sample that was shown was from the upper part of the lower unit. Yep, Peter.
Quick comment on the question and answer. In the Southern Rocky Mountain volcanic field, where there are crystal poor rhyolites integrated in crystal-rich dacelites, dacelites all show this kind of zoning, the rhyolites do not.
Yeah, that's yeah. So that's one of the key points that I wanted to make. That it does seem different, and that this is a characteristic that's not unique to the Caetano tuff, but in fact many of the rhyolitic ash flow tuffs in the Great Basin share these same characteristics. Something that defines a different end member in terms of the major paradigms that have been established.
So for our last talk, we move to Kamchatka with Ilya Binderman.
Well, good afternoon. So I will talk about the largest caldera-forming eruptions in Kamchatka, which is an ongoing effort for the past several years. And what you can see on this picture is the largest Holocene caldera in Kamchatka, the Kuril Lake, 8,000 years, erupted 8,000 years ago. And this caldera in itself is enclosed into the much larger caldera for which I will describe. So this picture is a courtesy of Vera Ponomareva. The Holocene volcanic record in Kamchatka is very well established, arguably the best in the world. So here you can see the 10,000 years of explosive volcanic activity in Kamchatka, starting from the glacial moraine 10,000 years ago. But when we consider Pleistocene and the older volcanic products, these are severely affected by the glaciation and by the active tectonics. As a result of the field work for the past several years, we were able to identify ignimbrite units which are not associated with visible calderas nearby, and ignimbrites which are associated with calderas. Oops. So just to look at this dramatic picture, there's a interaction of glaciers and ignimbrite eruptions, multiple calderas flooded by moraines, and again ignimbrites on top of the moraines. So this is the maybe the most volcanically active with respect to silicic magma area in the world because of the very fast convergence rates. Okay, well, I should mention that this is the Silicic caldera in Kamchatka, which has actually an overlapping 6 calderas, and it hosted the glacial lake, which escaped through this valley. So when we consider the isotopic value of Kamchatkan ignimbrites, we notice that this interaction between volcanism and glaciation is reflected in abnormally low delta Caetano values of almost all eruptive products erupted for the past 2 million years. The majority of ignimbrites in Kamchatka are below the what is normal delta Caetano value for igneous products. And I should also mention that the crust in Kamchatka is Cretaceous to Eocene, and it is actually abnormally high delta Caetano with respect to it, a lot higher than normal crust elsewhere. So there is a very significant several per mil depletion in volcanic products. And maybe Kamchatka represents a nice laboratory to investigate interaction between hydrothermally altered materials and shallow crustal petrogenesis, because the crust is so severely fingerprinted by glacial meltwaters. Okay, this is the result of dating, argon dating of major caldera-forming ignimbrites in Kamchatka. The fast convergence rate here leads to the largest concentration of eruptive products per unit arc length. So the other processes which likely affected and clustered volcanic activity is multiple glaciation which happened in this area. I just mentioned the oxygen isotopic evidence, but there is also ongoing investigation of moraine, including the sediments offshore of Kamchatka, suggesting that the last glacial maximum was particularly dramatic in causing large-scale volcanic eruptions. So when we put these new ages into the versus spec map for a foraminifera record, we observed that the majority of volcanic eruptions actually happened during the maximum glacial period. Counterintuitive. So the normal expectation would be deglaciation should promote caldera formation and increase volcanism. Here, it's exact opposite. We define the parameter 75% glacial, meaning that that's 75%, 25% of this peak would correspond to the 75% glacial cover. So how can we explain that? So the SPECMAC climate record is affected by bioturbation, so we are not able to resolve individual features within each glacial cycle. But if we look at the ice core record for deuterium isotopes or oxygen isotopes, the glacial time is actually the most dynamic time where glaciers would advance and retreat, and the amount of ice will change by as much as 50%. So we try to model it with Adelina Guillier at Barcelona, and the best solution for that would be if you hydrothermally alter the volcanic edifice, make the rock weak, and then build up structures which will collapse gravitationally during the interstadial periods, and that would create a positive feedback for major caldera-forming eruptions. Okay, but today I will report on preliminary data which we have for two of the largest supervolcanic sites in Kamchatka. This would be the Pouzetka caldera here. In the beginning of the talk, I showed the Kuril Lake caldera, which is a little bit older than the Crater Lake, but in terms of volume, it's about 3 times that, and the lake is a little bit bigger. Okay, and the Karimshina caldera, which is located here. For comparison, these are the caldera areas. And you can also notice Gareli caldera, Apala caldera, some famous Kamchatkan calderas of fairly decent size, and the Ksudich caldera, which I showed in the beginning. So these two calderas, by the way, represent maybe the n-member cases of potential petrogenetic models for arc volcanism. In Pouzetka caldera, we have a single collapse event. We dated different ignimbrite lobes and also zircons in hydrothermally altered tuff within the caldera in the drill core. They are all identical age. So this ignimbrite came out of the blue. There is nothing which indicate any precursor silicic activity in this area. Just a large volume ignimbrites, maybe 400 cubic kilometers, hard to exactly estimate, came from this area, mostly basaltic crust, which is 12 million years, 12 million years in age and older, up to Cretaceous. And this is the Kuril Lake ignimbrite, which is enclosed. Also, after a significant time gap, normal rhyolite erupted from here. So this Pouzetka ignimbrite is quartz-bearing, biotite-bearing, quite silicious ignimbrite. So last summer, we did a very challenging field work, climbing through these bushes. Here's the intracaldera, actually the caldera wall ignimbrite, which is chemically mildly zoned from being high silica rhyolite to low silica rhyolite, moderate crystal content. Okay, it contains sinters, no evidence of precursor volcanic activity, just xenoliths from the basement. And you can see also the caldera floor and the resurgent dome. So the caldera walls are being currently dated, and they appear to be much older, and there is no evidence, again, for precursor silicic activity in the area. Okay, so this one is 1.6 million, and caldera is 0.4 million years old. So this being determined. And the Resurgent dome is 200,000 years old, and it's mostly dacitic, but becoming more and more basaltic. So again, the system is becoming more and more basaltic. Okay, the caldera floor is a former glacial lake. So the whole caldera-forming eruption likely happened during the maximum glacial conditions. So the isotopic values are oxygen 18 depleted for the post-caldera sequence, including the Kuri Lake eruption. The caldera-forming ignimbrite itself, originally we thought it's normal delta 18O, but now we discovered that it's not. So the summary for this large caldera-forming eruption is that it's largely bimodal, basalt rhyolite. There is no intermediate product so far. Very spontaneous eruption of ignimbrites at these two periods. Built on thin basaltic crust and has low to moderate crystallinity and has hydrothermally altered sinters. Okay, the next caldera is a Karimshina caldera, which may represent a different end member of Kamchatkan volcanism. So it's shown here. It's severely dissected, and only the intracaldera ignimbrite remains. So here you have a rather significant pre-caldera activity spanning several million years, but the ignimbrite itself is 1.78 million years, and this activity, which ranged from basaltic to dacitic to rhyolitic, is actually significantly older, 1 million years older than the caldera-forming eruption. Again, there are no very clear pre-caldera magma within a million years or so. So again, this magma represented in this case by rhyolite, coarse-bearing rhyolite, came very rapidly as a single cooling unit. So you can see this very thick ignimbrite unit, which has identical age on top and at the bottom. And the pre-caldera volcanic products span a rather significant range of silica and potassium, and which is coincident with the regional trend for volcanism in this area in general. So the caldera-forming ignimbrite is displaced with respect to potassium to lower concentrations, and post-caldera intrusions, which are here, the post-caldera intrusions shown here as a black by black symbols are exclusively high silica rhyolites. But again, these high silica rhyolites, which trace the caldera rim, they erupted at least 1 million years later after the caldera-forming eruption. So it would be nice to explain everything by a single magma chamber slowly building up and then creating a large mashy magma chamber and then erupting and then sweating out high silica rhyolites from the ash, from the mush. But geochronology currently does not support this model. Okay, isotopically, there is quite a bit of heterogeneity of pre-caldera intrusions, which could be explained by interaction of high delta 18O crust in the area and low delta 18O sinters, which are present there. Similar trends occur for strontium and neodymium isotopes. So the caldera-forming ignimbrite is more homogeneous, and the most homogeneous are high silica rhyolites, which are intrusions, which are post-caldera intrusions. So the hydrogen isotopic value of biotite are the lowest ever measured in Kamchatka, and amphiboles and biotites are minus 160 per mil delta D. And the isotopic value for zircons versus the ages demonstrate for both for Karimshina, there are low delta 18O zircons, and there are some high delta 18O zircons very close to the eruption age. For Puzhetka caldera, which I showed in the beginning, all zircons are lower than the mantle, and again there is a little bit of xenocrystal contamination, but the majority of zircons are within the eruption age, very close to the argon-argon eruption age. So essentially, these are the two types of large volume silicic arc volcanism in Kamchatka. In one case, you get bimodal crust, rapid eruption of high silica, quartz-bearing rhyolites, and then nothing for the next 400,000 years. And then here, in Eruption caldera, you get slow buildup of silicic magmas, but again, it's not, it's unlikely to be liquid all the time. It's geochronology, again, does not support that. So I would like to propose a very speculative idea that hydrothermal preconditioning of the crust leads to leaching of alkalis from the roof rock. And when you add the sinters and the roof rock to the magma, it increases the melt fraction and it increases the silica concentration. And it also helps us maybe reactivate the magma system. And that would nicely explain the oxygen isotopic results and hydrogen isotopic results which I presented. So the common theme for these two calderas that we have assimilation of high silica, low delta TNO, and low delta TNO sinters. There's evidence for punctuated generation of rhyolites, not as continuous generation. So it's unlikely that there's a large batholiths under Kamchatka, marshy or less marshy. So it's more likely there's a network of dikes and seals, and there's a rapid generation, differentiation, and eruption of silicic magmas. Sometimes it leaves nothing in the crust, like in the case of Petrologic caldera, or very little in the crust, and sometimes it leaves something in the crust, and this needs to be reactivated by subsequent melting and additional fractionation. So, thank you.
I suppose we can indulge in one or two questions. No questions? So thank you again to all our speakers for those very interesting talks. Thank you.